or path like that. That's a Calc 3 calculation, I suppose. So we define f of z equal to the integral. I guess I need to say, so I'm on a disk D with center z naught. I'm going to define f of z to be the integral over, I think, the downward part, f of w dw. And so here's explicitly, that's the union of this this horizontal path that goes from here to here, and this vertical path which goes from here to here. All right. So this is x naught plus iy naught. This is x plus iy. All right. Great. Then we want to show that f prime of z exists. So we consider the difference between f of z plus delta z and z. And I'm keeping the delta z small enough so that the z plus delta z is within the domain that we're looking at here. And all right, so this is that by construction. And then I bring the minus in here to, like, you know, reverse the curve. And then I traded this union that for that. So this is gamma u that goes from z to z plus delta z. Which I hope I have a picture for that. I might not, though. Oh, I do. Yay. All right, so there's the picture for it. So I'm going gamma d plus delta z, and then minus the gamma d, which just gives me the upper. Oh, I always get lost in these when I'm trying to explain it. Sorry. Any event, so we're able to replace the sum of the blue and the red paths by the green path, is what it boils down to. But then, of course, you know that the integral around this for f is 0. So I'm guessing we're going to use that next here. Come on. Come on. Why won't it go down? Oh, there we go. So f of z is just a constant in the integral. So I have the integral over the upper path of that is just the integral from z to z plus delta z dw, but that's just delta z, right? And so we have f of z delta z for that integral. And so then I add 0 to the integrand here. So that was just this and that before. And so then the integral of the f of z dw I've already done up there. That's this f of z delta z. But then we're left with f of z, f of w minus f of z over here, like that. And now I use the ML theorem, which we proved last time, right? So the length of the upper curve is twice the delta z. Well, it's less than twice delta z. And I set m to be the supremum of the values of this on the curve. So then I can use the ML theorem, and I get this is less than ML, which is in this case 2m delta z. Putting that all together, I get the difference quotient for big F minus f of z is less than or equal to 2m. But as delta z goes to 0, you can see that the m, right, as delta z goes to 0, this m is going to do what? Like as delta z goes to 0, this just becomes a point, which makes these points the same, which makes m 0. So delta m goes to 0 as delta z goes to 0, which then proves that, in fact, f prime, big F prime of z is little f of z. Furthermore, we assumed little f of z was continuous, hence f prime of z is continuous. Because f prime of z is equal to f of z, right? Consequently, f of z is both holomorphic and possesses continuous derivative f prime of z, so we can apply corollary to 7.35 to Cauchy's generalized integral formula to see that f prime prime of z exists and is continuous. Yay, so that's Morera's theorem. So I'm sorry if I lost you in the path chasing, but it's not, if you sit and stare at it for 10 minutes, you'll get it. It's nothing terribly deep there. It's just tracing out the path. Now this right here is a proof that you will never see, I don't think, anywhere else in undergraduate math. There's a technique used in this proof which is very interesting. And I don't remember ever seeing it except here in my, I didn't have complex undergrad though, unfortunately. But so anyway, so Goursat's theorem says this. It says if f of z is a complex value function under domain D such that it's complex differentiable at z naught, all right? And that exists at each point z naught in the domain, then f prime is continuous on D. So this is the theorem which makes the thing I circled in green unnecessary. This theorem says that if it's differentiable, it's automatically continuously so. And so here's how the proof goes. It's based on Morera's theorem, among other things. So you let R be a closed rectangle in D with sides parallel to the coordinate axes, and you divide R into 4 identical subrectangles. You let R1 be the subrectangle for which the integral over the boundary of the rectangle is the modulus of that is largest among the 4 subrectangles. And then you observe that the boundary, that the integral around that subrectangle's modulus has to be greater than or equal to 1/4 of the integral around the whole boundary. Because it's the maximum one, right? So if you think about it, if you've got 4 and R1 is the largest one, then it can't be more than 1/4 of the whole thing. So equivalently, that gives you that the integral around the rectangle is less than or equal to 4 times the integral around the subrectangle. And then you do it again. Do it again. So let me draw, here's the picture, this will help. So we start with the rectangle R, and then you find R1 in which the integral of f of z dz around the rectangle is largest. The modulus of that integral is largest. And then you go in here, and you find the subrectangle of that on which the integral around the subrectangle is largest of the 4 subrectangles. All right? And then you look at R2 and you divide it into 4 subrectangles, and you find the subrectangle, the blue one, which the integral around that subrectangle, the modulus of that integral of f of z dz is largest. And you just continue in this fashion forever and ever. Amen. And so here's a step. Ultimately, when you're to the nth subrectangle, you have that this is less than or equal to 4 to the n times that. Now that does not look very hopeful as proving anything converges, right? You've got a 4 to the n sitting up here. That would make me doubt myself pretty severely if I come up with this idea. But magic happens next. Because not only is that large, the size of the subrectangle is also getting rather puny, right? So if you look at it, the length of the perimeter of R is L divided by 2n. The length of the boundary, on the other hand, is, where'd I put it? I'm guessing here. Maybe L divided by 2 to the n is the length of the, oh, there it is. L divided by 2n is the length of the boundary then. Whereas if L is the, I'm saying, suppose L is the length of the perimeter of R, then L divided by 2 to the n is the length of the perimeter of Rn. So, but we are assuming f of z is complex differentiable, right? Which means we have control over this difference quotient minus f prime. We can make that as small as we like, right? We can make epsilon n as small as we like in that. In particular, we can choose epsilon to be small enough for each n such that we bound this by that. And if we do that, you know, that's good. Notice that the g of z, by the way, equals to f of z naught plus f prime of z naught times z minus z naught. This is an antiderivative, right? You can integrate this, right? F of z naught times z and f prime of z naught times like 1/2 z squared minus z naught z, right? Here you go. So we have that the integral of g of z dz is equal to 0. By the way, this is not a circular argument. I have a footnote. You might think I'm using Cauchy's theorem here, which assumed continuously differentiable in the theorem, right? But I'm not actually using that continuity here. We have continuity of the derivative of g automatically from the context here. So anyway, so I have this integral, which is equal to this, because this integrates to 0. It's less than or equal to this over here, which ends up being 2L squared e to the n epsilon sub n divided by 4 to the n. We applied the ML estimate. Excuse me. So returning back up to star, put it all together, we have this is less than or equal to 4 to the n times that integral, which by the ML theorem is this. The 4 to the n's be canceling, and we just have 2L squared en, but we can make epsilon n as small as we like. Therefore, we have this is equal to 0 for an arbitrary rectangle. Then by Morera's theorem, that implies that the derivative is continuous. But that rectangle is arbitrary. Therefore, we have continuity of the derivative inside the domain. This is Morera's. This is Goursat's theorem. So, yeah, this is not one I would make you prove on the test. I mean, I think when I saw Dr. Folt do this in complex analysis, I was like, whoa, wow, that's a really ingenious argument. And I think this is I don't know what the genesis of this argument is. I think it's in Churchill's complex analysis. So my notes are loosely based on Gamelin. Gamelin hates this theorem so much. He doesn't think it's interesting. When he defines complex differentiation, he builds continuity of the derivative into the definition of holomorphic. So he essentially makes it impossible to state this theorem in his book. He hates it so much. Nevertheless, Gamelin's a great book, just it doesn't like this issue because it feels like this is not something we should be talking about to the first class. I don't know, but his book is for the second class anyway. Whatever. Anyway, so there you go. These are the major theorems of integral complex analysis. So like we'll pick up next time. So I've skipped past things if you noticed. I didn't do FTC1 for the complex integral yet, so we need to do that. We need to go back and talk about Leibniz's theorem, which is nothing more than applying the ML estimate to Cauchy's generalized integral formula. That actually has very interesting results. And of course, we'll do some examples. So anyway, we're almost caught up. I usually spend more time on these proofs, so my apologies.